Machining is the most versatile and accurate of all manufacturing processes in its capability to produce a diversity of part geometries and geometric features. Casting can also produce a variety of shapes, but it lacks the precision and the accuracy of the machining. In tandem machining, a single point cutting tool removes the materials from the rotating workpiece to generate a rotationally symmetric shape. The tool is fed linearly in the direction parallel to the axis of rotation to generate cylindrical geometry. Machine tool is called the lathe, which provides the power to turn the part at a given rotational speed and to feed the tool at specified rate and depth of cut. The types of the cuts are the facing, the contour turning, the chamfering, the parting, and the threading. The rotational speed in the turning is related to desired cutting speed at the surface of the cylindrical workpiece and given by the equation. The N is the rotational speed, the V is the cutting speed, and the DO is the original diameter of the work part. The turning operation reduces the diameter of the work from its original diameter DO to the diameter DF as determined by the equation based on the depth of the cut D. The feed in the turning is generally expressed in millimeter per revolution. This feed can be converted to a linear travel rate in millimeter per minute by the following formula. The FR is the feed rate in millimeter per minute. The F is the feed in millimeter per revolution. The time to machine from one end of the cylindrical part to the other end is given by the following equation. The Tm is the machining time. The L is the length of the cylindrical work part. The volumetric rate of the material removal can be most conventionally determined by the following equation. The RMR is the material removal rate in cubic millimeter per minute. A variety of other machining operations can be performed on the lathe in addition to the turning. These include the following: the facing, taper turning, the contour turning, the chamfering, grooving, forming, parting, knurling, threading, drilling, and other related operations. Basic lathe used for turning and related operations is an engine lathe. It is a versatile machine tool, manually operated, and widely used in low and medium production. The term engine dates from the time when these machines were driven by steam engines. There are four common methods used to hold work parts in turning. These work-holding methods consist of various mechanisms to grasp a work, center it, and support it in position along the spindle axis and rotate it. The speed lathe is a simple construction than the engine lathe. It has no carriage and cross-slide assembly, and therefore no lead screw to drive the carriage. The cutting tool is held by the operator using a rest attached to the lathe for support. A third lathe used to be a manually operated lathe in which the tailstock is replaced by a turret that holds up to 6 cutting tools. These tools can be rapidly brought into an action against the work one by indexing the turret. In addition, the conventional tools use an engine lathe is replaced by a four-sided turret that is capable of indexing up to 4 tools into position. The bar machine is similar to the chucking machine except that the collet is used instead of the chuck, which permit a long bar stalk to be fed through the headstock into the position. At the end of each machining cycle, a cut-off operation is separated the new part, and the bar stock is then going to be indexed forward to present a stock for the next part. The bar machine can be classified as a single spindle or multiple spindle. A single spindle bar mechanism has one spindle that normally allows only one cutting tool to be used at a time on the single work part being machined. The multiple spindle bar machine are available. These machines have more than one spindle, so multiple parts are machined at the same time by multiple tools. For example, a 6-spindle automatic bar machine works on 6 parts at the same time. At the end of each machining cycle, the spindle, including the collet and the work part, are indexed to the next position. Boring is similar to turning. It uses a single point tool against the rotating work part. The difference is that the boring is performed on the inside diameter of existing hole rather than the outside diameter of existing cylinder. In effect, the boring is internal turning operation. Boring machines have features in common with the turning machines. Lathes are sometimes used to accomplish the boring. The boring mill has a horizontal or vertical axes. Drilling is a machining operation used to create a round hole in a work part. This is contrast to the boring, which can only be used to enlarge an existing hole. Drilling usually performed with a rotating cylindrical tool that has 2 cutting edges on its working end. This tool is called the drill or the drill bit. The most common drill bit is a twist drill. The rotating drill feeds into the stationary work part to form a hole whose diameter is equal to the drill diameter. The drilling is customary performed on drill press, although other machine tools can perform this operation. The cutting speed in drilling operation is the surface speed at the outside diameter of the drill bit. It is necessary to remind the rotational speed of the drill. In this equation, the N is the spindle speed in revolution per minute, the V is the cutting speed, the D is the drill diameter. The feed can be converted to a feed rate using the same equation for the turning. In this equation, the Fr is the feed rate in millimeter per minute. The rate of the material removal is determined as the products of the drill cross-sectional area and the feed rate. Drill holes are either through holes or blind holes. In the through holes, the drill exits the opposite sides of the work, and in the blind hole, it doesn't. The machining time required to drill a through hole can be determined by the following formula. In the blind hole, the depth d is defined as the distance from the work surface to the depth of the full diameter. Thus, in the blind hole, the machining time is given by the following formula. A in both equations is the approach allowance and given by the following formula. Several operations are related to drilling. Most of the operations follow the drilling, where a hole must be first done by the drilling, and then the hole is going to be modified by one of the other operations. Centering and the spot facing are exception to this rule. All of the operations use a rotating tool. Reaming is used to slightly enlarge the hole, to provide a better tolerance on its diameter, and to improve its surface finish. The tool is called a reamer, and it usually has straight flutes. In the tapping, the operation is performed by a tap and is used to provide internal screw threads on an existing hole. The counter boring provides a stepped hole in which a larger diameters follow a smaller diameter partially into the hole. In countersinking, it's similar to the counter boring, except that the step hole is a cone shaped for the flat head screw and bolt. Centering, also called the center drilling, this operation is to drill a starting hole to accurately establish its location for the subsequent drilling. The tool is called center drill. Spot facing is similar to the milling. It's used to provide a flat machine surface on the work part in a localized area. Milling is a machining operation in which the work is fed past a rotating tool with multiple cutting edges. The axis of the tool rotation is perpendicular to the feed direction. The cutting tool is called the milling cutter, and the cutting edges is called the teeth. The machine is called the milling machine. The milling is an interrupted cutting operation, and the basic milling operation creates a planar surfaces. However, other geometries are possible. There are two basic types of the milling operations. The first one is the peripheral milling, and the second one is the face milling. Most milling operations create geometry by the generating of the shape. In peripheral milling, or also called the plane milling, the axis of the tool is parallel to the surface being machined, and this operation is performed by the cutting edges on the outside peripheral of the cutter. Several types of the peripheral millings are the slab milling, the slotting, the side milling, the straddle milling, and the form milling. In face milling, the axis of the cutter is perpendicular to the surface being milled, and machining is performed by the cutting edges on both ends and the outside periphery of the cutter, as in the peripheral milling. Various forms of the face milling are exist. This including the conventional face milling, partial face milling, the end milling, the profile milling, the pocket milling, and the surface contouring. The cutting speed is determined at the outside diameter of the milling cutter. This can be converted to a spindle rotation speed using the formula that should now be familiar. The feed rate in the milling is usually given as the feed per cutter tooth and is called the chip load. It represents in the size of the chip formed by each cutting edge. This can be converted to a feed rate by taking into account the spindle speed and the number of the teeth on the cutter as follows. The FR here is the feed rate, the N is spindle speed, the NT is the number of the teeth on the cutter, and the F is the chip load in millimeter per tooth. The material removal rate in the milling is determined using the products of the cross-sectional area of the cut and the feed rate. Accordingly, if a slab milling operation is cutting a workpiece with the width W at the depth D, the material removal rate is given by the following equation. This neglects any initial entry of the cutter before the full engagement, and this equation can be applied to the end milling, side milling, face milling, and other milling operations. The time required to mill a workpiece of the length L must take into account the approach's distance required for the full engage of the cutter. First, consider the case of the slab milling. The A value is given by the following equation, where the D small is the depth of the cut, while the D capital is the diameter of the milling cutter in millimeters. For face milling, let us consider the two possible cases. The first case is when the cutter is centered over the rectangular workpiece. The cutter feeds from the right to the left across the workpiece. In order for the cutter to reach the full width of the work, it must travel an approach distance which is given by the following relation. Here, the D is the cutter diameter and the W is the width of the workpiece in millimeters. The second case is when the cutter is offset to one side of the work. In this case, the approach distance is given by the following relation, where the small w here is the width of the cut in millimeters. In either cases, the machining time is given by the same equation. The milling machines must provide a rotating spindle for the cutter and the table for fastening, positioning, and feeding the work part. Various machine tools designed to satisfy these requirements. To begin with, a milling machines can be classified into a horizontal or vertical machines. In horizontal milling machines has a horizontal spindle, and this design is well suited for the performing of the peripheral milling, like the slab milling, the slotting, the side and the straddle milling, on a work part that are roughly cube shaped. The vertical milling machine has a vertical spindle, and this orientation is appropriate for the face milling, end milling, surface countering, and the die sinking on relatively flat work parts. The machining center is a highly automated machine tool capable of performing a multiple machining operations under computer numerical control in one setup with minimal human intervention. Workers are needed to load and unload the parts. It usually takes a considerable less time than the machine cycle time. So one worker may be able to tend more than one machine. The typical operation performed on the machining center are the milling and the drilling, which use a rotating cutting tools. Typical features that distinguish the machining center from the conventional machine tool and make it so productive include the multiple operation in one setup, the automatic tool changing, the polish shuttle, and the automatic work part positioning. Shaping and planning are similar operations, both involving the use of a single point cutting tool moved linearly relative to the work part. In conventional shaping and planning, as a straight, flat surface is created by this action. The differences between the two operations is, in shaping, the speed motion is accomplished by the moving of the cutting tool, while in the planning, the speed motion is accomplished by the moving of the work part. A single-edge cutting tool is used in interrupted cutting operation in both shaping and the planning. Subject tool is impact to loading when entering the work. Typical tooling is going to be a single-point high-speed steel tool. Low cutting speeds due to the start and stop motion. Shaping and planning can be used to machine shapes other than the flat surfaces. The restriction is that the cut surface must be straight. This will allow the cutting of the grooves, the slots, the gear teeth, and other shapes. Special machines and the tool geometries must be specified to cut some of these shapes. An important example is the gear shaper. The project is performed using the multiple teeth cutting tool by moving the tool linearly relative to the work in the direction of the tool axis. The machine tool is called the projection machine, and the cutting tool is called the proje. The projection is highly productive methods of machining, and the advantages are the good surface finish, close tolerances, and the variety of the work shapes possible. The project can be classified into a vertical projection machine and horizontal projection machine. The vertical projection machine is designed to move the proje along the vertical path, while the horizontal projection machine has a horizontal tool path. The projection also can be classified into internal and external projection. The projection presses, used only for the internal projection, that is pushes the tool through the work part. Sewing is a process in which a narrow slit is cut into the work by a tool consisting of a series of narrowly spaced teeth. Sewing is normally used to separate the work part into two pieces or to cut off the unwanted portion of the part. These operations are often referred as a cut-off operations. Since many factories require the cut-off operations at some point of the production sequence, the sewing is an important manufacturing process. The hack sewing involves the linear motion of the saw against the work. This method of the sewing is often used in cut-off operations. Band sewing involves a linear continuous motion using a bandsaw plate made in the form of the endless flexible loop with the teeth on one edge. The sewing machine is the bandsaw. Circle cold sewing uses a rotating saw blade to provide the continuous motion of the tool past the work. The circular sewing is often used to cut along bars, tubes, and similar shapes to the specified length. In abrasive cutoff, the abrasive disc is used to perform the cut-off operations on hard materials that will be difficult to sew with the conventional saw blades. In friction sewing, a steel disc is rotated against the work at a very high speeds, resulting in a friction heat that causes the metal to soften sufficiently to permit the penetration of the disc through the work.